If you are live streaming, we are logging back in on the other end, so we'll get started in a minute or two.
I think we're back. Can you hear us, Adina?
Yeah, can you hear me okay?
All right, yeah, we can hear you. Okay, so hopefully that doesn't happen again. All right, I think we're good to go.
Awesome, thanks so much. All right, hello, good morning, everybody. I hope you guys are doing well. And for those of you at home today, I hope you're feeling all right and recovering from whatever it is that you may have. I thank you for your continued masking in class to help try to stop the spread of all the things that are going around UMass right now. A couple quick announcements. So today we're going to be finishing the last section from chapter 1 called periodic functions. And on Thursday, we'll start chapter 2, but that means that our chapter 1 quiz is coming up. So the chapter 1 quiz is going to be on Moodle, just like the mini quizzes. And it'll happen on Monday. So it'll be open the full 24 hours on Monday. So it'll open at 12:01 a.m. and go until 11:59 p.m. And the assessment, you have 1 hour to finish it. There are 10 questions that are multiple choice, similar in structure and difficulty to the mini quizzes. So it's just sort of a longer mini quiz that covers all of chapter 1. So I would recommend in terms of preparation that you go over your old mini quizzes, make sure that you understand anything you got wrong. You are welcome to come to Drop-In Help and ask questions about any mini quiz that has passed. Then also making sure that your notes are organized. So just like the mini quizzes, the chapter quiz is open notes, your handwritten notes. So if you are organized, you can reference those. And then going back to the homework and just making sure that if there are any questions you are really unsure about, that you ask about them prior to the chapter quiz. So if you do all those things, you should be in pretty good shape for that chapter quiz on Monday. And again, you can take it at a time that's most convenient to you. So I'll talk a little bit more about that on Thursday, but I just wanted to remind you that that is coming up. I also want to remind you that this week, Williams reviews are on sine and cosine. So today we'll be talking a bit about sine and cosine within our lecture. But if you don't remember sort of the basics of sine and cosine from pre-calc, if it's been a while, it might be worth stopping by and checking out the lecture, looking at some graphs of sine and cosine, talking about common radian values, where they come from, things like that. And of course, I will post the recording after Thursday up on Moodle. So if you can't make it, you can watch the review on Moodle. Okay, so those are the things that are sort of announcements. Other than that, I think we are ready to roll. So as I mentioned before, we are going to be doing the last section in chapter 1, which is called periodic functions. So we're going to go ahead and switch to the dot cam. Okay. So there's a lot of different types of periodic functions. So we're going to start with just sort of the general idea of what is a periodic function, how do we recognize a periodic function, and sort of why do we even care about periodic functions, right? So let's start with just the general definition. So a periodic function is any function that repeats its values in regular intervals. And those intervals where the period repeats is called the period. So that's like it repeats every so often. So there's a lot of different types of periodic functions that come up in science and in data and all sorts of things. And the reason why they're so important is because if you have something that you realize has a pattern, that lets you predict what will happen in the future, right? So if you're seeing this pattern and it's always repeating, then you can say, well, that tells me that this is where this function is going to be at this point in time, right? Because there's a pattern, it keeps repeating. So that's super helpful for predictive analysis, which is really pretty powerful. So sometimes people recognize trends in things like the stock market or in science and how atoms are moving, and they're able to sort of figure out different things that are incredibly important because the function is repeating. So we're going to start with just a couple pictures of periodic functions to give you an idea of what I'm talking about. So here in this first function, I've sort of made this a solid line, this piece right here, but you can see that the pattern keeps repeating, right? And it was repeating before and it will repeat after. So if I wanted to try to keep going with this picture, I could just follow the pattern and keep repeating it, okay? And like I said, here in this piece right here, right, this would be one period because this is when I start repeating. Then this is the next period, then the next period. Similarly, right, here we have another periodic function, right? We got the big bump, then the little bump, then the big bump. So I know if I was going to keep drawing it, I draw a little bump and then a big bump, right? And then finally, the last one, this is a function from physics that has to do with our planets, right? You can see this one has a lot more bumps to it, so it takes a little bit longer to kind of look at it. But if you look at it, you realize eventually you sort of have big bump, come on down, and then over here, big bump, come on down. And you can see that it has this pattern, right? So one of the ways that we identify periodic functions is by graphing them or graphing the data we have and looking to see if we can visually see a pattern repeating itself. Now, sometimes that's really easy and sometimes that's really hard. And sometimes it depends on the person. Some people can find patterns much easier than other people. It really just depends on what you're looking at, right? But if we can determine that something's periodic, there's a lot of things that we can, I have the hiccups, I'm sorry, that we can find out that are helpful to analysis and to thinking about what this function tells us, okay? So the two sort of most general pieces that we're looking for once we see that a function is periodic are going to be what's called the amplitude and the period, okay? So starting with the amplitude. The amplitude is sort of a weird concept, and I will try to illustrate the amplitude as we go through today's lecture so you can sort of understand what I mean when I talk about this. But the amplitude is going to tell us how far we vary from the midline of a function to reach the extrema. So what does that mean? So when you have a function, there's a middle, right? And we're talking about the vertical direction here. So if we were to draw a line through the middle, how far do we have to go from the middle to get to the maximum y value? And how far do we have to go down to get to the minimum y value? That's called the amplitude. So it's a variance type of measurement. And the way that we determine the amplitude for any function is we find the maximum y value, we subtract off the minimum y value, and then we divide by 2. Okay, so that's how we calculate it. And so from there, that's going to tell us how much we vary from the midline. And like I said, I will show you what this looks like on the picture in a few minutes when we look at an example. The period of the function is the amount of time or distance, if that's what you're measuring, in terms of the independent variable that it takes the function to complete one cycle. So what that means is now we are looking at the horizontal change. How long does it take until we start to repeat? Now, we can totally do this visually. Later on, we'll learn how to do this more algebraically. But what we're doing is we're looking for the pattern and we're saying, how long does it take until the pattern starts again, right? And so we do that with the independent values. So the difference between these two is that the amplitude is looking at the up and down change and the period is looking at the left and right change, okay? So let's look at an example together and then we'll try some separately. But let's start with this picture that we had before, and let's talk about the amplitude and the period. Now, when you have functions that are just pictures that don't have like, you know, an actual algebraic function with it, we're going to be approximating the amplitude and the period. And so that means we just want to get close enough. So as we do some of these approximations, this one's a little more straightforward, but if yours is a little bit off from what I get, that's totally fine. Because when you have weird data pictures, it's not an exact science. So what does this look like? So for the amplitude, what I'm trying to figure out is where is the maximum? So the max is here. Where is the minimum of my function? That's here, right? And I could have picked any max and min, but these are closest to the scale. And so I want to figure out what these values are. So I'm going to call this max 3, and I'm going to call this min -1, and we are subtracting for our formula. So we have the max minus the min divided by 2. So we have to be a little bit careful when we do this because we're subtracting a negative. So 3 minus -1 is 4 over 2. 4 divided by 2 is 2. So the amplitude here is 2. And so I want to draw a picture for you to sort of describe what that means visually. So the midline of this function, right, if I were to find the exact middle, is roughly here. Okay, we're not going to be calculating the midline, but it's a good visual. And so the amplitude here is how far I have to go from the midline to get to the maximum value. which is 2, and how far I have to go from the midline to get to the minimum value, also 2. So that should be the same, right? Because we're finding it's the same in either direction. So that's what the amplitude is telling us, how far we vary from the midline to get to an extrema. Okay, so now the second thing we want to talk about is the period. So the period is how long it takes the function to repeat. Now you can do this from any part of the function until it repeats. So you could go from peak to peak. You could go from low to low, but you just have to pick a point and then figure out how long it takes to get to the starting point of the next one. So I'm just going to go over the part that I had darkened, and I'm going to use that to figure out the period. So here, if I'm looking at this part of the function, then it starts to repeat again. I'm going to count. So this is -1, -2, -3 is where this starts. And then over here, this is 1, and this is 2. So this is where it ends. So my entire function goes from -3 to +2. So that is 5 units before it starts to repeat again. So my period here is 5. Now, like I said, you don't have to do this the same place that I do. You could go from peak to peak, right? So the peak here is -1. The peak over here is going to be 1, 2, 3, 4, right? So this was at -1. This was at 4, right? So again, that is also 5 units. So it doesn't matter what point you pick. You're just picking a point that's convenient to you and seeing where then it starts to repeat. And that is called your period. So again, the period is a horizontal number we're measuring, and the amplitude is a vertical number that we're measuring. Okay, so I'm going to have you try this on the next 2 functions. They're a little more messy. I'll highlight some of the key numbers for you. But again, it's not an exact science. So it's sort of like do your best. So as long as you're sort of close to what everybody else is getting, you're in good shape. So this axis, we're counting by 2s. So this is 4, this is 2, this is -2, this is 4. Over here, this is 2, 4, 6. So hopefully that's enough to give you a good idea about that. And then you can get them both squeezed in here. On the bottom axis, try your best. This is 10, 11, 12, 13, 14. I don't know if you can see that. I tried to darken them up a bit. And then here we're just counting by 1s. So 1, 2, 3, 4, 5. And then -1, -2, -3, -4. And this will be -5 in this scale. Okay, so just take, I don't know, 2-3 minutes. Try to jot down what you think the amplitude and period are going to be approximately. Again, it doesn't have to be exact, just a relatively good guess, trying to use what we just talked about. Okay, so try it out. Feel free to check with someone next to you. If there's TAs there, they can walk around, and then we'll go through it together.
Hey, Dina.
Yeah.
The second graph is actually not really showing up that well. So you have to be able to trace. I know it's a little bit of a big long one. Would you be able to trace some of it? Oh, awesome. Yeah, that shows it very well.
All right, take about 30 more seconds to finish whatever part you're working on. All right, so let's take a look at these. So starting with the first one, if we're trying to figure out the amplitude, we need to figure out the maximum and minimum Y values and then divide by 2. So the maximum, there's a couple of them here, right, that repeat, but I'm going to use the one closest to the axis just because I think that's a little bit easier, and the minimum, right? So here and here. So we have to approximate these, right? It's not an exact science. You may not approximate exactly like I do, but if you're close, then that's fine. So I looked at this and I thought, this looks to me like it's going to have a maximum of 2.5. If you said 2.5 or if you said 3, that's fine. Somewhere in that range, roughly, maybe 2.3, I don't know, whatever you said, somewhere between sort of 2.2 and 3. Anything in there for a max is fine. And then for my min, I said, okay, to me that looks like negative 0.5. So you may have said negative 1, negative 0.75, but something in that area. And then we're going to divide by 2. Okay, so again, when we subtract a negative, we got to be really careful. Those are going to cancel each other. So we end up with 3 over 2, which is going to give me an approximation for amplitude of 1.5. Now, again, depending on the numbers you use, it could be anywhere from 1.25 up to 2. As long as you're somewhere in that general range, you are good, right? You shouldn't be getting something like 30, but in the sort of 1 to 2 range is where you should be landing, okay? So that's my amplitude based on my approximation. And now for my period, I have to look at where and how this function begins to repeat. And so again, there's no one right way to do this. I usually like to start at 0 if there's not something more obvious to me, but you don't have to. And for me, it makes sense because I can go from peak to peak. So when I was trying to figure out my period, I just went from peak to peak. And I tried to figure out what that distance was, right? And so by starting at 0, that's helpful just because then I measure to whatever that X value is, which here gives me 6 units. So I approximated the period to be approximately 6 units. Okay, so again, amplitude, vertical, period, horizontal. Okay, let's take a look at the second one. Second one's a little more tricky here, in my opinion, just because of the way it looks. So for the amplitude here, again, I'm looking for a max value. This is the one closest to the scale. So I'll use that one, but there's more of them as they repeat, right? And then also a min value. So I'm going to use this one. That one seems the closest to the axis. So here I'm going to approximate my max value to be 4, right? Because this was 0. So 1, 2, 3, 4. That's pretty darn close. And then this one I'm going to approximate to be -4. And again, you may not have exactly the same thing. You may have said 3.5 or something like that. But as long as you're close to 4 in some general direction, you should be good to go. We have to divide by 2. Again, careful with the negatives. We end up with 8/2, which gives me an amplitude of 4. Okay. So now for my period, I have to think about when this starts repeating. Okay. So if I start at 0, I want to get to the point where I'm at the same level, right? And so here, this is where 0 is. So to me, that is where it starts again, right? A little bit past this minimum. And so the piece that I'm looking at, I'm going to roughly trace, looks approximately like that. Okay, so here I started at 10, not at 0. So I have to be careful about that. And I go till about here. And so I'm going to approximate that to be, I don't know, 11.6 roughly. You might call it 11.7 or 11.5, which is fine. But to go from 10 to 11.6 gives me 1.6 units that I have to move until I repeat. Be a little bit careful since this is not 0. The period is not 11.6 because that would be the distance from 0, but instead from 10 to 11.6 gives me 1.6 units. Okay, and again, these are approximations. So if you get 1.5 or 1.7, that's close enough for these types of visual interpretations. Okay, so in this class and in other sort of math classes you may take in particular, there's 2 periodic functions that are particularly important to us. And they're important to us because they come up in weird ways in nature and in business that we don't expect. And sometimes we can fit models to them. You may have predicted this earlier that this might come up, but we are going to talk specifically about the periodic functions sine and cosine. So one important note that I want to make here in terms of this class, whenever we are doing any computational things with sine and cosine, which we won't really do a ton of here, but later on, if you're doing like sine of 5 or whatever in your calculator, everything we do is going to be in radians because we are considering the functions of sine and cosine and not the geometrical interpretations. So we're not going to be looking at angles in this class. So if you are doing problems with sine and cosine and you're getting them wrong, it may be that your calculator is in degrees and it needs to be in radians. So checking your calculator at some point to make sure it's in radians for the future computations that we'll do. Okay, so first let's talk about sine. So we want to talk about both the general characteristics of sine, but also things like the amplitude and period, right? So things that we've been talking about in terms of periodic functions. So sine is a periodic function that goes on forever. So if you were to keep going, it would just keep repeating the same pattern over and over again in both directions forever and ever. Other important hallmark characteristics of sine before we talk about the amplitude and period is that sine varies between 1 and -1, right? So when you graph it by itself, it just goes between 1 and -1. And sine starts, when I say starts, at the origin, so when it goes to 0, sine starts in the middle of the function. So if we were to draw the midline at 0, sine starts in the middle. Okay, that's going to be important later because one of the things we're going to be doing today and in the future is looking at pictures and saying, is this sine or cosine? And if it's just sine or cosine, people often recognize it. But once we start doing things to it, like rotating it or stretching it, it gets a bit harder to determine if we're looking at sine or cosine. So here we just want to remember sine starts in the middle. Okay. Regular sine starts off increasing, rotated sine would be decreasing, but we'll sort of get to that later. Okay, so let's look at the amplitude and the period of sine. So the maximum value of sine we know is 1. The minimum value is -1. So sine varies between 1 and -1. So my amplitude, 1 minus -1 divided by 2, is 2 divided by 2 which is 1. So the amplitude of sine is 1. And again, that's how much we vary from the midline. The midline here happens to be the 0 line. So we go up by 1 unit to get to the maximum and down by 1 unit to get to the minimum. Okay, now the period of sine. So here, if you think about when we start repeating, that happens here. And so the period of sine is a little bit past 6, and that's not a coincidence. The period happens to be 2 pi for sine. And so pi is 3.14 approximately. So 2 pi is 6.28 approximately. So you can see you're a little bit past 6. So when you're dealing with sine functions, if you have something that crosses a little after 6, it's pretty safe to say that that's 2 pi. Okay, so the period is 2 pi. Okay, now the counterpart to sine, the other function we'll look at, I'm sure you've guessed, is cosine, partners in crime. Sine and cosine are actually the same exact function shifted. Okay, that means that cosine is going to have all the same properties of sine, other than it's been moved left or right, depending on what you did. So let's talk about cosine, some of the hallmark characteristics of cosine, and then the amplitude and period. So I want you to notice here that at 0, where we typically are going to start looking at a function, that cosine starts at a maximum. Okay, remember sine started at the midline, cosine starts at a maximum. So if you are evaluating a function and you look at what's happening at 0, if it starts at a maximum value for the function or a minimum value of the function, then we're dealing in cosine. So if it's a maximum, you have just cosine. If it's a minimum, you have negative cosine because it's been flipped around. Okay. So again, that's one way that we use to determine if we're talking about sine or cosine when we're trying to create a model. So just like sine, the maximum value of cosine is 1. The minimum value of cosine is -1, which is the same, which means our amplitude is going to be 1. So here again, from the midline to get to the max, we have to go 1 unit. To get to the min, we go 1 unit. Similarly, if we look at the cosine function and when it starts to repeat, if you go from peak to peak, we're a little bit past 6. This is the same as sine, but the period is 2 pi. So both sine and cosine have the same amplitude and period, okay? Which again makes sense because they are exactly the same function, just moved over, which doesn't impact how long it takes to repeat or how far we vary. So we have to do some work with sine and cosine to get used to how we change it, how we look at it, what we do with it, in order to get to the point where we can start talking about the types of things we're going to be doing. That may not make sense right now, but it will in a minute. Okay, so what I want you to do is here, both of these graphs just have a picture of sine on it. Okay, so it starts at the midline and it goes until a little bit past 6. Same thing here, starts at 0, right at the midline, and goes to a little bit past 6. What I want you to do is I want you to use what you learned about graphing transformations last week to sketch on the same axes 6 times sine. So what does that 6 do to our sine function? What would the new function look like? And then similarly, I want you to come up with a graph of 3 sine minus 2. So what would the function 3 sine minus 2 look like? So obviously we're multiplying by 3, shifting by 2. What does that look like in relation to the original sine function? So I'm going to give you 3 minutes to try to think about what the new graph will look like. And if you have a graphing calculator, you can certainly pull it out and check by graphing this new function and sine to see if it's what you said it was. Okay, so feel free to check with someone next to you and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's start with 6 sine x. Okay. So as a reminder, when we multiply a function by a number, it stretches it or shrinks it depending on what that number is. If the number is bigger than 1, we're going to stretch it, which is what we have here. So that means that we're multiplying every single y value by 6. So in order to graph this, what I did is I started with the zeros, because 0 times 6 is still 0. So I plotted those in. And then I went to the maximum and minimum values to help give me the shape of the graph. We know that sine has a maximum of 1, so that 1 became a 6, because 1 times 6 is 6, so it's 6 times higher. Similarly, I came over here to -1, and I multiplied by 6 to give me -6. So I know that it has to go down 6 times as much to -6. And so then I was able to sort of sketch out what that would look like, making sure that I go through the zeros as I go. So what has happened is I've stretched this by 6 units to get 6 sine of x. Okay, let's look at the second one. I did the second one in 2 steps. So here there's 2 different things happening. First, we also have to stretch this, but now by a factor of 3. And we have to shift it. So when you add or subtract something at the end, it moves it up or down. Since we're subtracting here, we're going to be moving it down. So before I moved it down, I started with the 3 sine of x. I thought, what will that 3 do? So that's my green graph here. And I did the same thing I did for 6, but with 3. So I started with the zeros. And then I took the max value and bumped it up to 3, and the min value and bumped it down to -3. And then otherwise, it has to have the same general shape. So I stretched it by 3 in both directions first. And then when I was trying to look at what the -2 would do, it's going to move the whole graph down by 2 units for every single point. So I took those zeros and I moved them all down to -2. That was the first thing I did. Then I took that max, which was 3, and I moved it down 2, which gave me 1. I took the min, right, which was -3, and I moved it down to -5. And then I had plenty of dots to connect, because essentially I had to keep a 2-unit difference between the green and the red to move everything down by 2. So I shifted this green one down by 2 units at every point to get my final graph here of 3 sine x minus 2. Okay, so this directionality is one way that we look at sines and cosines, where we are shifting them and stretching them just like we did with the other functions as before. The other sort of direction that we're going to be headed with this, which is why we did this little check-in point here, is that sometimes we start with a graph like the red one, and we have to figure out what the function is. Okay. Now that is, in my opinion, quite a bit harder, right? If you have a picture and you have to figure out what the function is, there's a lot of pieces there to say, okay, well, what was the original function? What did we do to it? How did we, did we shift it? Did we multiply it by anything, right? So that's where the idea of amplitude and period come in when we're looking at sine and cosine, okay? Trying to think if I want to do the next one. We'll do this one together. So this particular function, okay, sine of x plus pi over 2. So this is another transformation we could do. And so here, right, if we have pi over 2 on the inside, this is going to shift left. So remember, when you add or subtract something on the inside, that moves it left and right, and it's counterintuitive to the direction. So since we added pi over 2, that would mean we were shifting this function left by pi over 2. So pi over 2 is a little bit past 1, so that's actually roughly here. And if we were to shift it left by pi over 2, we would move this maximum to the origin. This one I find incredibly difficult to do, but there is a point to it. So I'm going to go to the next page where I have it done out. Okay. When you shift sine left by pi over 2, you get cosine. So I said before, sine and cosine are the same thing, but shifted. If you shift this left, you get cosine. So I want to point out that 2 pi is approximately here. So if you start from 0, you can see that this is the sine graph, right? Starts at 0, goes up, then down. And this is the cosine graph. It starts at a max, comes down, and goes back up. So this causes a lot of problems for us in a lot of ways, because if I'm asking you to describe a particular graph and find its function, there are correct solutions for sine and cosine, right? Because you can always just shift it and get the other one. So what we're going to agree upon is sort of a norm of how we do this, is that we are not going to shift our answers left and right when we're trying to figure out sine and cosine forms. We're going to take whichever form makes the most sense based on how it starts and not shift left and right, okay? Because they are the same graph and there are infinite solutions, and that makes things complicated, okay? So what does that even mean? How do we start beginning to think about how to write an equation for a picture that we've done a bunch of transformations to? So we start with what's called the general form. Now, this is only going to be done with sine and cosine because it's periodic and because the properties of amplitude and period make sense for this type of work, okay? So the general form for sine, we have y sine bt plus c, and for cosine, a cos bt plus c. What does this mean in terms of the things we've been looking at and the things we're doing? So the amplitude for both these functions is going to be the absolute value of a. And the reason why that's true is because we notice that the amount that sine and cosine vary from the midline is the same for sine and cosine, and it has a unit of 1, which means if we're multiplying something here, all it does is stretch it in both directions the same amount. That amount is a. Since we report amplitude as a positive number, we take the absolute value of a to get the amplitude. Now, it's really important that we notice that this is the absolute value, but that when we're coming up with our equations, a could be positive or negative, right? So if we know that the amplitude is 5, when we come up with our equation, that means this could be 5 or negative 5, and we have to figure that out based on the picture that we're seeing, okay? We're going to come back to period in a second, but let's talk about the vertical shift. So this number that we add on at the end represents our vertical shift. So if it's positive, you move up that many units. If it's negative, you move down that many units. Now, because we vary from the max to the min the same amount, right, for sine and cosine, and the midline is at 0, this gives us a formula to help us find this vertical shift pretty easily. So we do y max plus y min divided by 2. Now this should look familiar. This looks almost exactly the same as our amplitude formula. The difference is that for vertical shift, we add these values together, okay? With amplitude, we are subtracting them. So because the base midline is 0, this formula works, which means this will only work when we're talking about sine and cosine. Okay. Now, finally, we need to talk about the period. The period is a little more complicated here because we have to figure out how this relates to b, because the b in our equation is what's going to change what's happening horizontally. So when you multiply something inside this function, it will either stretch it horizontally or shrink it horizontally. And so the period is going to be 2 pi over b. So what does that mean? That means if we have the function, we can take b and find the period by plugging it in here, okay? If, however, we have a picture, we can find the period and plug it in on the left-hand side to solve for b. So remember, the period is how often we repeat. So where you plug it in depends on the information you have. So here, if you have the information about the period from the graph, you plug it in here. If you have it from the function in general form, you have this number from the function, you plug that b in here. So you can find the period if you need to, if you have b, or you can find b if you're trying to create a function by plugging in the period. So with these 3 pieces of information, we are going to be able to look at functions and determine their formula in terms of sine and cosine. And again, this is only going to work for periodic functions for sine and cosine, but this is really powerful because a lot of things when you plot their data end up in this form. So being able to do this, really important. So these 3 things, plus the other piece of information we're going to need is it sine or cosine? Okay, so these 3 calculations plus sine or cosine is what we need to get these formulas. So we're going to try this on a bunch of functions. We're going to look at functions and try to come up with their formulas. But I want to remind you, sine starts at the midline, cosine starts at a max or a min. Okay, that's one of the things you should be thinking about when you think about this. And when I say start, I mean at x equals 0. So we're just going to try this. We're going to see what we can come up with. I'll tell you, it feels weird at first. It feels a little tricky, but the more you do them, the more you get used to it. So if it feels weird at first, hopefully by the time we've done 2 or 3, it'll feel a little bit better. Okay, so here's 2 functions. Okay, I want you to try to come up with a general formula for these 2 functions. So I recommend, whenever you're doing this type of work, to first try to determine if it's sine or cosine. That should be the first step. After you determine if it's sine or cosine, then you can work on the amplitude, the period, and if there's a shift. Okay, so again, it's weird at first. Feel free to check in with someone next to you. I'm going to give you about 4 minutes to try these 2 out, and then we'll go through them together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's take a look at these and see if we can find their general formulas. So what's helpful for me when I'm doing this type of problem is to really try to visualize what one period will look like, because sometimes they look really long and complicated. So I just try to think about one period. What am I dealing with? So here, when I think about what's happening at 0, I notice that I'm in the middle, right? I'm not a max or a min. And so if I'm in the midline, that gives me a clue that this is some sort of sine function. Okay, so again, if you start in the middle, we're dealing in sine. Now, I know from looking at the sine function before, let me see if I can show you again. Remember, sine looked like this. So this looks different, right? Because sine before was increasing and then decreasing. But in this picture, we are decreasing and then increasing. So if you have a sine function and you start off decreasing, that tells me I have negative sine because it's been rotated around the x-axis. So I'm dealing with a negative sine function. Okay. So that's sort of the structure that I'm going to build upon by considering the other things that are part of this. I also notice here that this function goes till a little bit past 6, which means that it's the standard 2 pi, which tells me that my b is 1, that I don't have to do anything on the inside because sine and cosine always go to a little bit past 6. So if that didn't change, I don't need to do anything to the inside here, which is helpful. Okay, so let's talk about the amplitude. So the amplitude, remember, I'm going to find the max value. I'm going to find the min value. So my max here is 3. My min is -3 divided by 2. I'm going to be really careful with my negatives. So I have 6 over 2, which is 3. And then I'm going to check my vertical shift. So I'm going to do max plus min divided by 2. 3 plus -3 is 0. So that means I don't have a shift if that comes out to be 0. And the period is 2 pi. So that didn't change anything, right? Because here what I would normally do is I'd say, okay, so 2 pi equals 2 pi over b, right? But b has to be 1 here for these to be equal. So there's an invisible 1 there all the time. So that means putting this all together, I have negative sine with an amplitude of 3. So I have -3 sine of x. My vertical shift was 0. My b was 1. So I didn't have to include anything special in there. So this function is -3 sine x. If I wasn't feeling super confident about this, I would graph -3 sine x on my calculator and make sure that it looked like this. right? It's a good way to double check your work. All right. Let's look at the second one. Okay, so similarly, when I do these, I like to try to envision just sort of one period. So it looks like it goes from here to here. Just gonna trace that. So what I notice here is that I start off at a maximum. Okay, so again, if I start at a maximum or a minimum, I'm dealing in cosine. If I start in a maximum, I'm dealing in positive cosine. If I started at a minimum, it would be negative cosine. Okay, but that's sort of my general structure that I'm working around. So when I think about my amplitude, I have my max value, which is 3. My minimum value over here looks like it's going to be 1 divided by 2. So I have 2 over 2, which is 1. My vertical shift, I'm going to do 3 plus 1 divided by 2, which gives me 4 over 2. That is not 0, so I do have a shift here, is positive 2. And then for my period, again, I see that I'm a little bit past 6, so that's 2 pi. This is going to be the same as last time. If it is 2 pi, that means your b is 1. So we don't have to do anything special here. So putting that all together, right, I have cosine of x plus 2. Okay, your amplitude is 1. If you want to put a 1 in front, that's fine. So you can remind yourself that that's what we found the amplitude to be. But typically anything times 1 is just itself. So we usually don't write the 1. Okay, so here we have cosine of x plus 2. So it got moved up. All right, I'm going to have you try one more of these types. This one's a little bit harder. Okay. But see if you can apply all the stuff we just tried to this particular function here. So this scale, in case you can't see it, that's 1, 2, 3, 4, 5, 6, 7. And this scale is 2, 4, 6 as you go up and down. Okay, so I'll give you 2-3 minutes. See if you can come up with the formula for this function. right, take about 30 more seconds to finish up whatever part you're working on. All right. So again, I want to start by trying to visualize what one period of this function looks like. And that looks like this. And I immediately notice that this doesn't go out to 6 like it did before. So I automatically know that something is happening with the period, but I'll come back to that in a few minutes. The other thing I notice here that at 0, this is starting at a minimum when I sketch this graph, right? And so again, if you start at a maximum or a minimum, we're talking about cosine. And so here, since we're starting at a minimum, we're talking about negative cosine. So that's the general structure we're building upon, because again, we started at a minimum as we look at our function here. So now we want to take into account all the other pieces we need. So let's start with the amplitude. So here, the maximum looks like it's at 4 minus the minimum is at -4 divided by 2. So we have 8/2, which is going to give me an amplitude of 4. My vertical shift will be 4 plus -4/2. 4 plus -4 is 0. So I know that the vertical shift here, that there isn't one, that I don't need to add anything at the end. And then the last part I have to figure out is the period. So again, since this happens a little bit past 3, I'm pretty confident that the period here is pi, right? If you're a little bit past 3, you're at pi. If you're a little bit past 6, you're at 2 pi. So what I need to do here for the period is take pi and set it equal to 2 pi over b. Because again, if I know the period, I need to use that to solve for b. So I'm going to multiply the b up and then divide the pi down, right? Which is going to tell me that b equals 2 pi divided by pi. The pi's will cancel, and b equals 2. So again, remember, b is what goes inside the function next to your variable. So putting that all together, I know I have negative cosine. So I have negative, now I need my amplitude, -4 cosine. My b is 2, so 2x, and my shift was 0, so I don't have to add anything on here. So I have -4 cosine of 2x. And again, if I wasn't 100% confident in my solution, I would graph -4 cosine 2x and make sure it looks like this. And then I would know that I had figured that out correctly. Okay. So that's, I would say 70% of what we do is we're looking at pictures of graphs and trying to determine how to write it in a cosine or sine form. But another way that we might see this is going to be in a word problem. Okay, so I want us to try a word problem just so we can see how we take that information and transform it into a model using sine or cosine. So here we have Boston averages 15 hours of daylight in June, 9.5 in December, and 12 in both March and September. Assuming that the number of hours of daylight varies periodically, so that word periodically helps us know that we're modeling in sine and cosine, over a period of 1 year. Okay, so notice that we have a period of 1 year. That's going to be important to us. Write an expression for n, the number of hours of daylight, as a function of t. Let t be in months and t equals 0 correspond to the month of June. Okay, so that's also important. T equals 0 corresponds to the month of June. The other important pieces are these numbers here, okay? So what I'm gonna do is I'm gonna give you about 3 minutes. I want you to try to see if you can come up with a sine or cosine formula based on what the data is here. And I would encourage you to graph this. So this is just a sort of blank graph, 0, 1, 2, 3, 4, 5. And then this is 1 through 19, using these values to see what the picture may look like so that you have a sense of if it's sine or cosine, and then see if you can figure out the formula from there. Okay, so take about 3 minutes and then we'll go through it together. All right, take about 30 more seconds to finish up whatever you're working on. All right. So when we approach this problem, there's a lot of different ways you can start it. It really just depends on how your brain sort of processes all the information. For me, I really keyed in on this time equals 0 corresponds to the month of June. So when I was thinking about a picture, I said, okay, so June is time equals 0. That's right on the axis. And so what I'm measuring here is the month versus the hours of daylight, right? So in June, I had 15 hours of daylight. So I plotted that. And then I sort of labeled each of the months along the way, because that helps me remember and to visualize what's going on. So I then plotted the other data points. So 9.5 in December, I approximated to be about here. Then I had 12 in March and September. So I went to September and did 12. I went to March and did 12. And then back here at month 12, we're back in June again. So we're back up here. So this helped me visualize the entire cycle. And before I even try to sketch anything in, I can see that I started at a maximum and ended at a maximum. And so I know from before that if I start at a maximum, I'm dealing in cosine, right? So I'm just gonna note that here. So then I was like, okay, if I know this is cosine, I can get a sort of rough visual of what's going on. It's gonna look roughly like this. So the other pieces that I know I'm gonna need are my amplitude, my period, and my shift, okay? So let's start with the amplitude. I'm just gonna call it A here. So the amplitude is gonna be the maximum value minus the minimum value divided by 2. I can see from my graph that my maximum value was 15, or of course I can get it from up here. My minimum value is 9.5 divided by 2. So if I do out that calculation, I get 2.75. Oops, my 5 looks really goofy. Okay, so my amplitude is 2.75. My vertical shift, I'm going to add these. So 15 plus 9.5 divided by 2. When I do that, I get, let's see, 24.5 divided by 2. That's going to give me 12.25 is my vertical shift. And then I need to figure out the period. So here from my graph, I see that my period is 12 months because that's how long it takes for me to repeat. So my period here is 12, right? I'm not dealing in pi here because I'm actually dealing with the literal number of months. So that means that I'm going to set 12 equal to 2 pi over b. I can multiply the b up and divide the 12 down. So my b is 2 pi over 12. I can simplify my fraction. 2 over 12 becomes 1 over 6. So now I have to put all of these things together. And so I start with my amplitude here. So I have 2.75 cosine, right? I know it was positive cosine because it was the max. Now I need my b, which is pi over 6. Now here, one of the interesting things here is the variable. So here I'm going to be using t because t is my independent variable. I'm going to put t in there. And then I have a vertical shift of 12.25. So this is the function that models this scenario. One key piece of information here that I think is really important for when you're doing homework is if you were to do this whole thing and get all the numbers right, if you used X here, you would be marked wrong on Wiley because we were specifically told to use a T here. So make sure you're using whatever variable is given to you in the setup for your solution. Okay. So typically in a problem like this, you wouldn't be given a graph, you would just be given the information, but you can always plot a graph out like I did to dot it out. That helps me understand how to do it, but if you can do the calculations without the graph, you can go ahead and do it algebraically, okay? On Thursday, we're going to be doing a lot of things with small numbers. Please bring your calculator with you to class. I'm going to show you how to plug things in with tables. All right, I'll see you then. Have a good rest of the day.